We're starting with this problem today, but it's actually bringing back a problem that we did previously. We've already figured out an equation for this. In our last lesson, we saw that we could do that because we first wrote an equation for area. We found that the area of the circle equaled pi r squared. And then we wrote an equation for what r equals. We found that r equaled 60t. Oops. And then we substituted the value in for r and found the derivative of that resulting function. Well, I want to show a different way that we could have chosen to approach it, just to bring it back to this idea of the related rates, finding the derivative with respect to time, all that kind of stuff. So I actually could have gone straight from my area equation into finding the derivative with respect to time. So if we did that, that would give me dA over dt equals 2 pi r. I love how the derivative of area is circumference. All right, so we got 2 pi r. Wait, I'm missing something. What am I missing? Yeah, we need to also then have the dr over dt. It's so easy to forget. So you got to remind yourself, put all those derivatives with respect to time in. All right. So now if I wanted to figure this out, notice what we're looking for is we're trying to find a description of the rate at which area changes. So that is going to be how the area changes over time. That's dA over dt. So if I want to be able to write this equation, dA over dt equals, well, 2 pi. What's my radius? Well, remember, that's the one where we don't know what it is at this moment because this is just a general equation for time. So that's going to be the 60t, because that's how we calculate what the radius is at any point. And then what's dr over dt in this problem? Well, think about what dr over dt means. Dr, and this is why I kind of like the d notation like this, because it tells you that it is how much is the radius changing over time. How is r changing as t changes? And notice that's what we're told up here. The radius is increasing by 60 centimeters a second. So then the dr over dt just equals 60. And so if I wanted to do it using this method, of course both methods work, but if I did it during there we go, this method, I'd multiply that out. That'd give me 7,200 pi times t, which is the exact same derivative function that we found yesterday, just using a different kind of a method. So why do I show it to you if we already found it? Because I want to show you how, first of all, this same method will give us the same answer, which is always a good thing. If in math you use two different methods and get two different answers, one of our methods at least is flawed. The other thing is just saying that we can apply these types of problems to these word problems, and that's actually going to be our big theme going forward. And so if we're going to start taking a look at these word problems, this is going to be our first big one where we're going to have to use related rates. So go ahead and take a moment and write down this whole problem so that as we do the work, you know where it came from and why we did what we did. So we got a big old word problem here, and there's a lot of different things going on in it, right? We got lots of different lengths, and we got a rate there. It's a matter of how do we pull this stuff together. Now, of course, a great strategy anytime you're doing a word problem is to find a way to kind of pull all the information into one place, kind of coalesce it all into one kind of idea. And a picture is a great one for that. And so if I drew a picture of this situation, I'd probably end up with something that looks about like this. So I've got my ladder leaning up against the wall. Mathematicians love ladders leaning against walls because they make right triangles. So it gives us an excuse to play with right triangles. So we got this ladder that's leaning up against a wall. We know the ladder itself is 10 feet long. And notice the bottom is moving outward at 1 foot per second. So I'm just kind of making note of that stuff. And so we do love right triangles because we have a beautiful little equation for right triangles. What is that equation that we love using for right triangles? Pythagorean theorem. And so I'm going to go ahead and represent this situation with Pythagorean theorem. Now, of course, you know Pythagorean theorem is a squared plus b squared equals c squared. So you now have to make a decision of how you're going to show your work. What are we going to call these different quantities? Do I want to go with a and b to fit with a squared and b squared? We can. The downside is I might forget halfway through the problem what I decided to make a and what I decided to make b. I tend to forget those types of things, so I'm not going to use a and b. From there, it's okay, how can we represent this then? Well, we got the height of it on the wall. There's really just one way to represent height here. There's not a whole lot of different names for it. The other quantity, though, can be given different names. In this problem, it's the bottom of the ladder. So you might use B for bottom. But to me, that doesn't make as much sense. Some people might also use B to represent like base. You could think about it that way. To me, though, it just doesn't make as much sense as W for width. So I choose to use W. But again, this is not hard and fast. Just choose a letter that works well for you and that makes the most sense for you here. Just choose letters that actually mean something relevant. So not A and B. All right. So let's start working through this. Let's see. The ladder's 10 feet long. Got that in there. The 1 foot, I drew that on there. The 6 feet. Okay, I should label that. The bottom of the ladder is 6 feet from the wall, so I'm just going to track there that W value is going to be 6 feet. All right, so it is Pythagorean theorem. I can now actually represent that. I'm going to start with the really general one. W squared plus H squared equals 10 squared. Yeah, I could actually even plug the W value in right now. It's just that, well, I'm not going to. Because in order to figure out what the rates are that are all involved in this, I'm actually going to have to cope with the rate at which that width is changing. So I'm going to have to leave the W in there right now so that I end up actually finding that rate as part of the problem. All right, so then, if rates are involved, that tells me I have to take the derivative, because remember, derivative is rate of change. And notice our rates here, it's measured in respect to time, which most rates are. And so that tells me, take the derivative of this equation that I just wrote with respect to time. Well, that's a familiar process, I hope. That's what we were just doing tons yesterday, what we did on last night's assignment. Let's go and take the derivative with respect to time. So the derivative of W squared is 2W. And I'm going to use the d over dt kind of notation. I'm not going to call it W prime. If you want to call it W prime, you can. But as I will hopefully mention here in a little bit, that actually lets us see a few other little things going on and helps us remember some stuff. So I like that notation, even though it looks more complicated. Plus, now I do the derivative of h squared. So that gives me 2h and then dh over dt. And then on the right side, the derivative of 10 squared. Yeah, I know it's squared, but isn't it still just a constant? And since it's a constant, the derivative is 0. All right, now looking at this equation, what do I really want to know? I'll go back up there, look and see, figure out what are we looking for. It's asking how fast is the top of the ladder sliding down. So when it's saying that, the quantity that it's talking about, how fast the top of the ladder is sliding down, we're looking for this rate. Notice that's how the height is changing. That tells me that what I want to figure out is what is dh over dt. In order to figure that out then, I need to know what all three of those other values are. I need to be able to figure out what's w, what's dw over dt, and what's h. Because if I know what all of those are, I can then solve it for the dh over dt. So now knowing that, I'm going to start grabbing numbers and plugging them in. And we'll just deal with what comes as it comes. So 2 times w. Do I know what w is?
6.
Yes, it is 6. That's the width, that's the base, that is 6. So I got 2 times 6 times dw over dt. That's another quantity I needed to know. Do we know what dw over dt is? Yes, we do, because, and again, a way to visualize it, this is why I like the dw over dt notation. To me, it makes a little more sense. When I see that, that's telling me how is the width changing over time. And so I look for something that gives me width per time. And up here, I'm told that the bottom of the ladder, that is the width, is changing at 1 foot per second. Notice it's a distance over time. So it is 1 plus 2 times h. Do we know what h is? Not yet, no. But can we find out? Yes. Because I can actually use my original Pythagorean theorem up here, and I can use that to figure out what h is. Because I know w. W is 6, so I'm going to do 6 squared plus h squared equals 10 squared. Now let's actually solve that for h. So of course we square both sides, or we square each term rather, and then I subtract what ends up being 36 from both sides, so that gives me h squared equals 64. Therefore the height must be 8. Obviously the height can't be negative 8, so we don't need to worry about the negative solution as an option. So I did a little extra calculation on the side there. I found that h was 8. dh over dt, do I know what that is? No. If I knew what that was, I would have just put that down as my answer, because remember, that was the part we were trying to figure out. So I just leave that as dh over dt. Now solve that equation for dh over dt. All right, so to solve that, it looks like we got a 12 plus 16 dh over dt, so I subtract 12 from both sides and divide by 16. 12 over 16 reduces to be 3/4. Notice we did subtract to get there, so it's a negative 3/4. Now let's talk units, because of course we have to know what our units are here. And a great way to know the units, this is partly why I really like the d over dt kind of notation, is that when I look at that, it's telling me here that my units even should be h over t. How is the height changing with time? So, what's height measured in here in this problem? Feet. What's time measured in? Seconds. So it's negative 3/4 feet per second. All right, so that's our final answer. What that answer just told us is that as the bottom of this ladder is moving outward at 1 foot per second, the top of the ladder is moving downward, because it's negative, by 3/4 of a foot every second. So the bottom is going out faster than the top is coming down at this point. Now, that'll change later, depending on which point we check this at, where the ladder is at any given point, how those rates are related will change some. And so we always have to do the calculations uniquely based on the exact position of what we're looking at, because there's so many variables. Having done that problem, you now should be able to do this one entirely on your own, because it's just a variation on the same kind of a theme. There's a couple little subtleties that we'll talk about to make sure you nail down, but go ahead and write down this problem and work it out on your own first. Now make sure you're heading off in the right direction. This is where you should have started. We write our equation. Again, it's another one of those right triangle problems that's formed by that ladder leaning against the wall. And so we find the derivative with respect to time so that we can actually consider the rate at which it's changing per time. As we get ready to plug in numbers, you hopefully found that h was 15. And that lets us get to this point. Now, I'm now at the point where I got to plug in for dh over dt, which is the value that we're given up here. But notice up here that this is the height and how the height is changing. The height is changing by 4 feet per second, but is that height getting bigger or smaller? It's getting smaller because it's sliding down. So when I plug in for dh over dt, I'm actually plugging in a negative 4 there, because we're decreasing by 4 feet per second. And then we can go ahead and solve this equation for dw over dt. And when we do that math to solve it out, you should be getting an answer of 7.5 feet per second. So, in other words, as the top comes down at 4 feet per second, the bottom of the ladder is going outward at 7.5 feet per second. All right, so we're going to tackle a new type of problem here. As you take a look at this problem and get it all written down, hopefully you're starting to kind of process through and starting to think, how would I approach it? Now, after having done the problems we've done so far and kind of the section we're in, which helps to prompt our minds in a certain direction, hopefully you're already thinking, okay, I'm going to have to write an equation, and then I'm going to have to find the derivative of that equation with respect to t. Because it's asking for a rate. Specifically, what tells me how I would need to approach this problem is really the actual question that's being asked. How fast is the area of the rectangle increasing? Well, that tells me I have to have an area equation specifically, and that it's that area equation that I'm going to be finding the derivative of with respect to time, because how fast requires knowing something in regards to time. All right, so then let's go ahead and start applying at least that information. Even if we don't know everything else, we at least know that much and we can go with it. So, area of a rectangle. Simple enough equation, right? Area equals length times width. And so, now I can go ahead and find the derivative of that equation with respect to t. In fact, this hopefully seems like a familiar derivative with respect to t because it actually came up on last night's assignment. This is the one where we end up having to use the product rule. So dA over dt equals, now product rule. Remember, product rule is original times derivative plus derivative times original. So that's going to be w and dl over dt. Alright, so that's my derivative using product rule. Now it's a matter of, okay, what can I actually do to solve it and find out my answer? Again, I'm going to start by trying to figure out which of these quantities, because you notice there's actually 5 different unknowns in this equation right now. Which of those is the one that I actually am looking for? Which one is my answer? Well, it's how fast the area is increasing, so that means it has to involve area, and since it's a rate, it also has to involve time. Well, that certainly narrows it down, right? Because it's got to be this one. This is the only one of those 5 unknowns that actually involves area per time. So that's what I'm going to try to figure out. So I can go ahead and put that part in right now, since it's all by its lonesome already. dA over dt equals, and now I'm just going to start plugging in values. And if I don't know what the value is, I'm going to go try to figure out what the value is. So L, do I know what L is? Yes. We're actually told that the length up here is 20 centimeters, so grab the 20. All right, so 20 times dw over dt. Do I know what dw over dt is? No. Yes, I do, because dw over dt really means the rate at which the width is changing, width over time. So the width is increasing at a rate of 3 centimeters per second. So that means this has got to be a 3 here. Plus. Now, that was just how the width is changing, so it was width over time. Now I'm putting in W. W is just what is the width. Not how's it changing, but what is the width right now. Are we told that? Yes. The width is 10 centimeters. So that's going to be a 10 right there for W. All right, and then finally, dl over dt. That is, how is the length changing over time? How fast is the length changing? Do we know that? Yes, the length is changing at 8 centimeters per second. So that's going to be an 8 there. Well, thankfully, this one's even easier to find our answer. We don't even need to do any algebra. It's just do 20 times 3, 10 times 8, and add them up together on the right-hand side. So that's going to be 60 plus 80, so that is 140 when we go ahead and do that multiplication and addition. Now, let's talk units again. Again, this is why I like the d over dt kind of notation, because it can actually help me know what my units should look like. My units are going to be the A units per the T units, or in other words, what's area measured in? In this case, we're talking centimeters for our length, so the area must be centimeters squared, or square centimeters, whichever way you say it. So it's centimeters squared per, now that was the top, right? So that was the area, so that's got to be over T, over time. Time here is measured in seconds. So it's per second. So our answer is 140 square centimeters per second. In other words, the area of this rectangle is increasing by a full 140 square centimeters every second at this point and at this current status of this particular rectangle.